All right, so about to take a quiz on this. So, first one, translated 5 units right, 4 units up, or 2 units up. 5 right, 2 up. So what would the vector look like on that? Yeah, it'd just be 5, 2, right? So we go 5 units right, 1, 2, 3, 4, 5, up 1, 2, down 2 over 1. So it should look like this. Okay, so in a translation we slide, right? Oh, got moved. Okay, number 2, reflection across the x-axis. Here's the x. So how far is A away from that line? 3. It's 3 above, so I'm going to throw it 1, 2, 3 below for A prime. D is 5, M is 5, W is 4. So it should look something like this. What do we do in a reflection? Flip it. Flip it over the line. Okay, now number 3 is like what we did yesterday. We're going to dilate by a scale factor of 2. So what's going to happen with this? Scale factor of 2 is going to get bigger or smaller? It's going to get bigger. Okay, so what are the coordinates of A? Is 1, 1. So remember, what do we do with the dilation? Just multiply everything by the scale factor, which is 2 in this case. So 1, 1 times 2 is going to be what? 2, 2. So there's my new A. What's the coordinates of B? 2, negative 1. So what's that going to turn into? Okay, good. If I multiply both of those by 2, it's going to turn to 4, negative 2 for B prime. And then what are the coordinates of C? Negative 2, 0. Multiply both sides by 2. What's that going to turn into? Negative 4, 0. So there's C prime. Oh, it should look like that. Okay, so in a dilation, okay, we're changing the size.
I'm so sorry.
All right, next one. So we want to know the scale factor. What is the scale factor? So the scale factor is the number you multiply to get the new one. So to go from here to here. So I'm thinking, all right, 2 times some number gives me 5. 2 times what is 5? 2 times 2 is 4. So that's not it. 2 times 3 is 6. So 2 times what gives me 5? Okay, so if you remember yesterday we did this. So if you just think about it algebraically, all right? The question I'm asking myself, 2 times something equals 5. 2 times something equals 5. 2 times something equals 5.
250.
So what do I do to solve for x? Divide by 2. That way these 2's cancel to 1. That leaves 1x or just x. And the answer is 5 halves if you leave it as a fraction. Or as a decimal, it would be 2.5. 2 times 2.5 is 5. Now in your quiz in just a second, the question that's like this, it's going to leave it in a fraction like this. Yeah, you can. I wasn't thinking you. All right. Next one. Rotation of 180 degrees. So what's the rule for rotation of 180? You just change the signs. You get negative x, negative y. All right, so what are the coordinates of V? It's 2, 0. So if we change the signs, it's going to be negative 2, negative 0. There's no such thing as negative 0, so it's just 0. So negative 2, 0. Actually, yeah. Okay, what's the coordinates of J? Is 1, negative 1. So if I change the signs on both of those, where's it going to be? negative 1, 1. What are the coordinates of r? Good. 4, negative 3. Change the signs on that. Negative 4, positive 3. And then what are the coordinates of y? 5, negative 3. So if I change the signs there, it's just become negative 5, positive 3. So it should look like that. Okay, when you do a rotation, which way does it go? Oh. Remember, it always goes counterclockwise. Remember, rotation always goes counterclockwise. Okay, so today we're going to talk about symmetry and tessellations. Okay, so this first type of symmetry is the type of symmetry that you pretty much know about. So is there a line anywhere I can draw through this star to like split it exactly in half? Yeah, split it symmetrically. Where?
Very top.
Okay.
Spike.
If I went like that, would that split that symmetrically?
Yes.
Yes. Would make these two pieces like mirror images of each other. Could I split it any more times than that?
Yes.
Okay. So I could split it right here. Could split it right here. And like right there. Can I split it any more than that?
Oh.
If I draw some other lines to split it symmetrically. Yes, actually I could, right? What if I split it like going like right through here? Would that split it symmetrically? And right here, and right here. Oh. Okay, so how many lines of symmetry could I draw in there?
A lot.
That's it. So how many is that? Well, it's not like crazy. I mean, you can count it really quick. Wait, and make sure you don't count the same line twice.
I got around 16. 16 or 17. 18.
Okay, so you have 1, 2, 3, 4, 5, 6, 7, 8. But then this line right here is that line already, right? So if I count this one, I'm counting the same line twice. So there's 8 lines of symmetry on this one. 8 lines of symmetry. Okay, on this triangle, could I draw a line to split it symmetrically?
No.
Nope. So on this one, there's none. There's no lines of symmetry on there. Okay, what about on this T cross-looking thing here? Could I split it? Okay, so I could go right here. Go right here. Can I split it anywhere else? Like right there. That would split it symmetrically. Could I split it anywhere else? No, I don't think so. So there's 4. Okay, so that's the type of symmetry that you used in the past. So there's other types. There's what we call rotational symmetry. So what rotational symmetry is, where you can rotate it and it lands back on top of itself before it just goes all the way back around. Okay, so like on this little design right here. So I'm gonna trace that on this patty paper. Okay, so I'm going to rotate it. Does it land back on itself there? Does it land back on itself there? No. I got to just go all the way back around to where it started from, right? So that means this has no rotational symmetry. Okay? No rotational symmetry. What about this flag? Does this have rotational symmetry? This one's a little bit deceiving, but you'll see it after I do this. Okay, so here we go. Spin it there. Obviously it doesn't match up there. Does it match up?
No.
It's close, but not there. So this one has none also. Okay, what about this like little X-Men looking thing here? Yes. Okay, so I'm just going to put a star up here so we'll know where the top is, where I started at. Okay, so does it go back to itself there?
Yes.
Yep. What about here?
Yes.
Yep. Here?
Yes.
Yep. And then all the way back to there. So the question is, how many times can I turn that and it land back on top of itself before it gets all the way back around? 4. And the other question is how many degrees do I have to turn it before it maps back onto itself?
90.
That's a 90-degree turn, right? Every 90 degrees it looks like it did originally, okay? So we say that this has order 4. There's 4 turns before it gets all the way back, and to each one it's 90 degrees. Okay, then what about on this rectangle? Yep. Okay. So it doesn't do it there. We got to get to there. So how many times can I turn this one? Twice. And how many degrees? 180. So if I do the same thing, put the star there. So it doesn't there. There's half the circle. That's 180. And then back around is 180 to get it back to where it started. Okay, now talking about three-dimensional figures, there's different types of symmetry. There's plane symmetry. So plane symmetry is basically where you slice a plane, like basically slicing a knife through it, and it makes 2 equal pieces, okay? And then there's symmetry about an axis where you put a line through the middle of it, and then you spin it on that axis, and it lands back on itself before it just goes all the way back around, okay? So let's think about this little pyramid right here. Could I slice that somewhere right down the middle and make 2 equal pieces?
Yeah.
Yep. Like if I sliced it like right down the middle right here. So this has plane symmetry. Like if you think of that as a piece of candy or something, take a knife, you could split it right in half and make 2 equal pieces. Okay, does it have symmetry about an axis? Could I put a line like go right through the very top up here and then go down through here and spin it on that line and it land back on top of itself before just going all the way back around? Yes, I can do it 4 times. So this has axis symmetry. Okay, what about this 3-dimensional L? Does it have plane symmetry? Could I slice it somewhere and make 2 equal pieces? Yes, if I sliced it like down like this, that would make 2 equal pieces. So it has plane symmetry. But could I put an axis through it somewhere? Like draw a line through it and spin it on that line?
No.
And you're right. No, there's nowhere I could do that. Okay? All right, now let's talk about tessellations for just a second. So a tessellation is a tiling. It's the repeating of a pattern that completely covers a plane with no gaps or no overlaps. So it's taking one shape or maybe even more than that, but what we're going to talk about is just one shape and just repeating over and over again and completely filling up a flat surface. Okay? So what's an example of a tessellation in this room? There's several.
Yes. 4 floors.
Okay, the floor is a perfect example. If you look at the floor, all those squares, they took the same shape and they just repeated that shape over and over again to fill up completely the floor. Where you can't see the concrete that's underneath there, all you see is the tile. The ceiling is a tessellation with those tiles. Definitely is. The blinds over there are basically a tessellation. It's one, like a bunch of rectangles.
The wall. The flag.
The flag, yeah. It's
The wall.
a bunch of stripes.
The wall.
Yeah, I mean, so you can see tessellations show up a lot. All right. So let's drop down here and look at this one. Okay. Could I take this little triangle and tessellate with it?
Yes.
Yes. Okay, so that's what I want you to do is we're going to draw another triangle the same size, but basically turning it upside down and fitting it like that. And taking another one putting it like that. Another one like that. Like that. Okay, so yes, you can tessellate with an equilateral triangle. Okay, now I'm going to scribble out this triangle because I don't want that there. Can you tessellate with a pentagon?
Yes.
All right, let me trace this out.
No, you cannot.
Okay. Can I tessellate with that pentagon?
Yes.
There's going to be a gap there. And am I going to be able to put another piece of a pentagon to fit in there? No. So there's going to be a gap. And that's the problem. On the tessellation, there cannot be any gaps or overlaps. Okay? So you cannot tessellate with the pentagon. Okay.
Like you yeah. And then make that picture.
Okay. On the back of the paper I just handed out, it's blank. Okay? Turn over to the back side where it's blank. What I want you to do is take that little hexagon that I just gave to you. Put it anywhere in the middle, just somewhere in the middle, and I want you to trace out that hexagon.
Man, I think I know to do this right.
Okay, so trace out that hexagon just right in the middle somewhere. You don't have to be exact, just somewhere in there. And what I want you to do is write out the word tessellation. 2 S's, 2 L's. Write the word tessellation inside of there. Okay, then what I want you to do is stack it next to there. Okay, so what I want you to do is I want you to go ahead and turn it over to the front side, answer those questions, and then when you get done with those, I want you to come back to the back side here, and I want you to cover up the back side of this page. I want you to tessellate the back side of this page with this hexagon. Okay, go for it. We've been doing this.